are now recording, and got the slide up. Do you have any questions on anything we've done up to now?
The due date of our test is...
What's that?
The due date of our test that you gave out.
Okay. We are almost through with 1.3. Yes, like very close to being through with 1.3. So when we finish that, which will be today, knock on wood, that then it'll be 1 week from today. Right. But if you need more time, you can have it. Just don't run it into the next test. I want to get them back to you so you can see anything you may have missed before I pass out the next test. All right. Good question. Any others? Okay. Where we left off last time, we had been talking about networks and sort of a generic sense. They could be traffic networks or, inflow, outflow on different problems, something like that. One particular model is an electrical network. And these follow a series of laws, basically two laws, and they're called Kirchhoff's laws. Okay? The first is a pretty simple, should make a lot of sense. The currents flowing into a junction must flow out of it. Okay, that's it. So the sum of the currents flowing into a junction has to equal the sum of the currents flowing out of that junction. You can't pile up current at a junction. It just doesn't happen. And number two, the sum of the products, IR, which is a voltage drop, I is current, R is resistance, around a closed path is equal to the total voltage in the path. Okay? So in other words, if you sum up the voltage drops around the closed loop, they've got to add to zero. Okay? So, now in an electrical network, the current is measured in amperes. That's given a symbol capital A. Does anyone know why it's a capital A? Ampere is named after Louis Ampere, okay, a French physicist who talked about and developed, they named the unit after him. R is the, okay, by the way, we have two things going on here, several different things. I was trying to see what they call it here, but they don't, so I'm going to call it anything I want to. We have any of you had physics already? You have. Okay. What did you call voltage in physics? What symbol? Capital V. That's also the unit. So you're not talking about the unit. You're talking about the symbol for voltage. Okay. Some texts call it E for electromotive force, which is not really a force. So that's why I was wondering. So you have voltage, which is measured in volts, which is rather strange because most of the time your parameter is one thing and your unit is something else. Here it's the same. Volt is also capitalized. Any idea why? Same reason. But it's a different name. Named after Alessandro Volta, who was an Italian physicist who made the first, studied batteries really extensively. He made some of the earliest batteries and studied them. So they named the unit volt after him, Volta, from Como, Italy. And my wife had professional meetings there one year, right the week between terms. So I got to go with her, and I got to tour around Lake Como, Italy, while she was busy in meetings. It was terrible. Okay. So anyway, your current, the symbol for the current is I, and my pen is dragging out. I don't know why. That's a capital I. That is just the parameter. It's measured in, see, I'm not even close to this. I don't know why it's doing this. Okay. Current is measured in amps. Okay. And resistance. Anyone know what resistance is measured in? Ohms. Where did they get the term ohms? A scientist, a German scientist named Georg Ohm. Okay, so they named the unit after him. So what do you think the symbol for ohm is? Okay, yeah, it's kind of like a horseshoe. You would think it would be the letter capital O, wouldn't you? Because that's what ohm starts with. Just like volta starts with V, ampere started with A, ohm should start with O. But why don't they use a capital O? It looks like a 0 to me, okay? So yeah, that would be confusing. If you had 5 ohms and someone read it as 50 something, you know, so yeah, that would be confusing. So usually when things get confusing, we go to the Greek alphabet. But in the Greek alphabet, the letter that corresponds to ohm, to O, capital O, would be capital Omicron, which is a capital O, okay? So you don't get any better. Except for the Greek alphabet actually has another letter in it. This is Travis, right? All right. 5 was my magic number in the last class, and it's the magic number in this class. Okay? There's another letter in the Greek alphabet that begins with O, but it doesn't correspond to the letter O because where it lands, it's actually, anyone know it? Omega, exactly. Well, I say it doesn't correspond to O. O is stuck in the middle after mu, nu, omicron, okay? Like M-N-O, okay? Where is omega in the Greek alphabet? The very end. It's the last letter in that. And what's the first letter? Alpha. Have you ever heard of the alpha and the omega? The beginning and the end, the first and the last. That's where that phrase comes from. So they use omega, okay? And that's, I kept seeing the horseshoe shape. See, I got the pen away from it for a while and talked for a while. It quit squiggling all around it. Now, here is a really dumb thing. It just shows how crazy physicists are, okay? Resistance is the resistance of current flow in a circuit. So you have to have voltage, energy to overcome that resistance and make the electrons move, or the charge carriers move. There is another number that sometimes physicists have liked to use, and that's conductance as opposed to resistance. Whereas resistance is resistance to flow, conductance is the ease of flow, okay? And it's simply just the reciprocal of resistance. Conductance is the reciprocal of resistance, okay? So what symbol do you think they use for conductance? Well, wait, yeah. This symbol, O, this represents a volt. Squiggling again. That's named after volta. This represents an amp, which is named after ampere. And this represents an ohm, which represents this symbol, resistance. So what unit do you think they use for conductance? Since conductance is the reciprocal of resistance, what unit do they use? You probably didn't have this in your physics class, but it is true. It really is true. What unit would they use for conductance? I don't know any guy who came up with it. They just started using it because it was convenient. So they decided to use the unit of a mho. Now that's what Larry and Curly, this is just a mho. Now where did they get that thing? Was it John Moe or something that came up with that? That's a weird spelling. Where did they get the unit mho? Any guesses? It's all spelled backward, exactly. Physicists are kind of nuts. So what symbol would they use for a mho? They can't really use M because that's used for meters, so that's already in use. What would they use? Symbol for a mho. And a mho is a reciprocal of an ohm. So what's that again? The letter mu. Good try, but no. They use that for something else. Here's the symbol for a mode. They just inverted an omega. That's not a symbol in anybody's alphabet, okay? They just inverted an omega. So physicists are kind of nuts, you know. I'm a physicist. Okay. All right, but anyway, that has nothing to do with what we're doing, okay? Now, let's give the relationship to these. And they just said it here. Electrical network, the current is measured in amps. That's what you're measuring there, current. The resistance in ohms, that's why I put that down, and the voltage in volts. Okay. Now here are some symbols we use. For a battery, which is, we're using direct current here, they usually use something that looks like that. You may have several of them. A long line followed by a shorter line. The long line indicates the positive pole of the battery, the short line the negative pole. Now you could have multi-cell batteries, so it could have 2 or 3 pairs like this written next to each other. Always the side with the long is the positive side. The short is on the other side. So that's a volt. Current, there's no really symbol for it. It's just a wire. Something going through the wire. We usually indicate that by a direction like that. Current flowing in that direction. Okay? Resistance has a symbol that looks like this. Now, occasionally they'll put a circle around it that represents a light bulb. Usually the resistor in the middle, the circle representing a light bulb. But that is the basic symbol for the resistor. Okay? And resistors don't have a direction to them. They can go either way. Okay? Now, like we said before, the product, and this, of course, comes from Ohm's law, the same guy Ohm, that V is equal to IR. Is that how y'all express it? Yeah, okay. Some books use E is equal to IR, okay, but I like V of phi, okay. So that means when you have, and basically, when you go across a battery, if you go in this direction, that's a plus whatever the voltage of that battery is, 12 volts, 2 volts, 3 volts, whatever. If you go that direction across it, you're dropping in voltage. You're going from the plus side to the minus side. When a current is flowing this way through a resistor, that's always a voltage drop. The battery supplies energy, the resistor uses the energy. So that's the voltage drop. If the current's going this way, that's a minus. If the current's going this way, but you're going this way, then that would be a positive IR. Because the IR, this is the resistor, there's the current, that's the voltage drop or increase, depending on which way you're going. The voltage supplied, positive if it's this way, negative if it's that way. So that's basically what you need for electrical circuits for Kirchhoff's law. Okay? So I'm going to do example 6 with these terms in mind. Here we have a juncture, 1. Okay? A junction. You can say it either way you want to. And we have going up from this, and you don't have to have right angles. This is just how they usually draw them. We run into a resistor, okay? Then we run into a battery, okay? Or a voltage power supply, okay? And with the long line that way, okay? And we go down here to another juncture, which they numbered number 2. We also have a line coming out of this one that runs into another resistor, and it just runs over to junction 2. We also have a line coming out of 1 that hits another resistor, okay, and it runs into a battery here, and that goes up to there. Okay. Now, let me fill in the blanks here. This we're going to call, or they chose to call, current 1. Okay? And they call this resistor 1. And they tell you this is a 3 ohm resistor. Okay? This is a battery. They don't give it a name or a number, but they just tell you it's a 7-volt battery. Okay? This is your resistor 2, and they tell you this happens to be a 2 ohm resistor. Okay? Oh, and by the way, they named this current here I2, just for reference. They have a resistor down here they call R3, and R3 happens to be a 4 ohm resistor. Okay? And they have a current here, which they're calling I3, and okay, this battery over here is an 8-volt battery. Okay. There is your circuit. Okay. Now there's no guarantee that this circuit actually works. We're going to see if it does. Okay. That's a pretty ugly I, isn't it? I3. Okay. Now, you're given to, oh, and what we're looking for here, what are the 3 currents? Notice they give us the values of the 2 batteries, they give you the values of the 3 resistors. What we don't know is the value of the 3 currents. So that's what we're looking for. That's going to be our variables. I1, I2, and I3. Okay? So guess how many equations we're going to need to determine that. To solve 3 variables, you'll need at least 3 equations. We're actually going to get more than 3, but some of those may be redundant or dependent equations on each other. The easiest thing to start with are your junctions. Then you can go about your loops. Okay? So let's try the first junction here. What can you tell me the way they chose to draw it? If I drew it right, no, I didn't. I'm sorry. Well, yours too, pretty small there. The I1 they showed going in the other direction. It's in that direction. When I first glanced at it, well, I got both of them wrong, didn't I? Okay. They showed I3 going this way. I got I2 right, I think. Okay. Okay. Yeah. Yeah. So, guess what? I think they got them right, but they could have the eyes in the wrong direction. If they do, what would be the result when you finally get your answer? The eyes would have been negative. That means turn it around. It's going the other direction. So we're assuming, but I'm suggesting they got them right. And here's why. This battery is pumping current that way. This one's pumping current that way. So these two have to be, or you would think had to be that way. So this one, since you got 2 coming in, you better have 1 going out. Okay. So I would say this is probably the correct orientation of your currents. Okay. Now, if one of those batteries is flipped around, oh yeah, you're going to have a little bit more problem figuring out. Okay. So let's take the junctions first. What can you tell me about this junction in terms of the currents? I1 is coming in. I3 is coming in. And I2 is going out. Is equal to I2, is that what you said? Okay. Or another way to say that, okay, is I1 coming in minus I2 going out plus I3 coming in, that has to equal to 0. Sum of the currents at any junction has to be 0. Okay? How about junction number 2? What would you say is happening there? I1 I1 is going out, I3 is going out, and I2 is coming in. That would be minus I1 plus I2 minus I3 is equal to 0. That's the same equation. So there's no reason writing that down. That's a dependent equation. That just repeats the same piece of information. We don't learn anything new from that. So now we go to the loop law. That's the junction law. Here's the loop law. Pick a loop, and you got 3 of them here. You can do a loop around here, you can do a loop around here, or you could try to do a loop around there. We only need 2 of them. Now they chose to do, and I think it makes the most sense, to do this loop and that loop. And notice how I drew showed my hands there, pointing my fingers. This seems to be going like this. The current's going in that direction. Notice it's leaving 2, going this way, and this is going toward 2. But this one down here seems to be going that way. Guess what? You can pick the wrong direction if you want to. It'll just tell you you're going in the wrong direction. You'll have a minus at the end. So don't sweat it, okay? So those are our 2 loops. To do the first one, since it's starting here, I would start at 2. You don't have to. You can start at 1. It doesn't matter. Starting at 2, going up here, what do you find voltage-wise here? Yeah, plus 7 volts. Okay? So I'm going to put the plus 7 over here. That's a constant, right? Okay? Now, what do you run into here? A voltage drop, because you're going across the resistor with a current. And how much would that be? Yeah, and R1 happens to be 3. So that would be 3I1, right? Now, since I've got the voltage on that side, the constant voltage on that side for this so far. That's on this side, since that would be a drop, but they're on opposite sides of the equation, that can be a positive. You got that? If it's on the same side, yeah, if you chose that to be positive, do this negative. But since I'm putting them on opposite sides of the equations, what I'm saying is my voltage drops equal my voltage gain. So that's going to be the same. So that was going to be an I1. So that was 3I1. That's a voltage drop. And what's your next one you run into going around this loop? Plus 2I2. Because 2 is the resistor here, I2 is the current, plus 2I2, and that's equal to 7. The voltage drop equals the voltage gain. Popped up by the thing. Okay? The second loop down here, I chose to draw it that way, because number 1 the book did, but actually better than that. It makes sense. If you leave 2 again and go through, what's the first thing you hit here? Plus 8 volts. So that's the voltage gain I'm going to put on the right-hand side. And then you have a voltage drop of 4I3. So 4I3, we'll put voltage drops on this side. And then you go through this one, and that's a 2I2. 2I2. And there, and those are added. Okay? So here we have 3 equations, 3 unknowns. Think we should do it? What would be the first thing you would do to solve that system? Do it, write it as a matrix. That sounds like a great idea to do in a matrix algebra class. Okay. What would that be then? 1, minus 1, 1, 0. Next, 3, 2, 0, 7. Next, 0, 2, 4, 8. Okay? Now, as soon as I wrote that, one thing popped in my mind. Anything pop in your mind? Yeah, divide the last one by 2. So make that a 1, a 2, and a 4. But let's do it a little bit neater than that. Okay? Make that a 1, make that a 2, and make that a 4. Okay. Let's get back to my pen. Now, what's the first thing you want to happen in a matrix like that? 1 in the upper left? Yay, we got it. Okay. Next. You want that to become a 0. How do you make that happen? Row 2 minus 3 row 1 will become the new row 2. Okay? So this becomes, we're using row 1, so we're not going to change a thing in it yet. 1 minus 1, 1, 0. We're changing row 2, and what does it become? What does it become? 0. I like it. Next. 5. Perfect. Next. -3. Next. 7. Very good. And your next row we leave alone. 0, 1, 2, 4. Okay, what's the next thing we want to happen? We want the first non-zero entry in the second row to also be a 1. It happens to be a 5. We have 2 options. Maybe more, but what 2 options do you see? Switch the row. Please do. Dividing by 5 would be the other option you introduce a bunch of fractions. I love my fractions, but not that much. Okay? So let's just walk into those. So, let's try it down here. Top row is 1, -1, 1, 0. Second row is now 0, and this is row 2 exchanges with row 3. Okay. 0, 1, 2, 4, and 0, 5, -3, 7. Okay. What do we want to happen next? Above and below. Let's do it. Above and below this leading 1. That's why we want a leading 1 there. We want a 0 up here and a 0 down here. So how do we make this one happen? Row 1 plus row 2. That should do it. And that'll be the new row 2. Okay? No, row 1. Row 1. Okay? So you add them and tell me what you get. 1, 0, 3, 4. Okay. Now we're using row 2, so we'll leave that one alone. 0, 1, 2, 4. Okay, that's our leading 1 row that we're using. What do we want to happen below it? The 5 become a 0, is that what you said? Okay, how do we make that happen? Okay, you may have been saying that, I couldn't hear. Okay, row 3 minus 5, row 2. Okay, and you tell me what we get then. 0, that's fantastic. 0, that's good. Okay. Yeah, minus 13. And -13. All right. You want to just pause right now and tell me what you see from row 3? You got to divide each of them by -13. And let me do it here. Watch me do this. Okay, I'll divide. How's that? Ooh, accept that. Okay, I did it. Just became 1, 1. What does that tell you? Right off the top. What did the third column represent? I3 is equal to 1, 1. Unit? Oh, come on, you have physics. Name that for Luis. Andre. I think it was Andre. Andre Ampere. Okay. I'm sorry. Luis was something else. Okay. So we have right now we know I3 is equal to 1 amp. We know that right now. So I3. Oh goodness, what are you doing? Where did my pen go? There we go. I3 is equal to 1 amp. Okay? Now, you got two options. What you want to do? Oh, okay. You're doing Gauss-Jordan elimination, which we started here. But since we know this, we could do back substitution. But let's go on and do 0 above and below. How do we make that 3 become a 0? Row 1 minus 3, row 3 is the new row 1. Okay? All right. So we're going to make a new row 1. So row 1 minus 3, row 3. What does that give us? 1, 0, 0. Okay. Say that again. 1. Okay. What does that tell us? I1 is also 1 amp. Ooh, wow. Okay. And next. Yeah, we want a 0 above that leading 1 in row 3, so right there. So what do we do to make it happen? Row 2 minus 2 row 3 is the new row 2. Okay? So that will be 0, 1, 0, second, 2, okay? 4 minus 2 is 2. And then we keep the bottom row 0, 0, 1, 1. So that tells us then that that I2 is equal to 2 amps. Okay. Let's see if this kind of makes sense. Okay, I1 was the current coming through that 7-volt battery through the 3 ohm resistor and into junction 1. We said 1 amp. I2 was the current, I3 was the current coming through the 8-volt battery across the 4 ohm resistor and going into junction 1. And then they added to be I2, which goes through the 2 ohm resistor. Okay? Well, it makes sense that 1 and 1 equal 2. Yeah, that works. And that your positive battery there goes through, drop, drop, and comes to 0. This one, positive 8, goes through there, drop, drop, and comes to 0 as well. It makes sense. The numbers are right. The relationships are right. That feels really warm and fuzzy. So, looks like it's a good answer. Let's see what they got. I1 equal 1 amp, I2 equal 2 amps, and I3 equal 1 amp. Don't worry, they're not always going to be that simple. Okay? Do you need this up a little longer? Okay? If not, let's go to example 7. As I said, they're not always that simple. All right, here we have a circuit. I'm going to start down here at 1 because it seems to be a good place to start. A wire leaves junction 1, goes up and hits a resistor, and then hits a battery, but is in reverse. I do mine a little more accentuated than theirs, and goes to junction 2. From junction 1 up to junction 2, we have another resistor. Okay? From 2, we go through another battery to another resistor, okay, to junction 4. Okay? Junction 1, we have another circuit leading out of here, going through another resistor, and going to junction 3. From junction 3, between junction 3 and 4, we have another resistor. And from 4, we have another wire leading out, going backward across the battery, and going down through another resistor. And that's our circuit. So I've numbered my junctions. Let's label my batteries. A 10-volt battery, a 17-volt battery, okay, and a 14-volt battery. Okay. Now let's pick some currents here. All right. I was having trouble seeing it first, but there's current 1, which they put the arrow that way, which I concur with. This is current 1. They say current 2 is flowing in this direction, which I will buy. That first resistor, R1, is a 2 ohm resistor. Okay. R2 over here, without D2, is 4 ohm resistor. Okay. Already labeled that one. R4 up here, through which I4 is going. Okay. R4 is 2 ohms. Okay. They say here from 4 is going toward 3 through, and that'll be I5, through a 2 ohm resistor. R5 is equal to 2 ohms. Oops, I don't know why I did that. Okay, oops, this R3 down here is equal to 1 ohm. Takes a long time just to draw the circuit. And this is I3 down here, I believe it is, yeah, I3. And they suggest it's going in that direction. I won't argue with them. And then we have a 14 ohm resistor, and they're suggesting, which I concur with, the current here, I6, is going that way with R6 is equal to 4 ohms. Now, let me say this. Just happens to be this time they have 6 resistors and 6 currents. Not necessary. You could have extra resistors or currents without a resistor in them. You know, they don't have to balance out like this. They just seem to be doing that this way, maybe for introduction purposes, just to keep it easier for you. But don't worry, you could have more currents, resistors than you have currents. You know, you could have 2 resistors on the same current. I mean, there's lots of things you can do there. Okay? Now, we have 4 nodes. I call them nodes, I call them junctions. And these are all separate. Well, are they? Yeah. Because this one has I1, well, I didn't list it there. That's I2. Okay. And I3 all deal with this one. Up there we have I1, I2, and I4. Over here we have I4, I5, and I6. Down here we have I3, I5, and I6. So you see, in this case, we don't eliminate one because we have the other one pretty simple. The 2 nodes, you know, they're exactly reverse of each other, not here. So in this case, I would do 4 equations with our currents. Well, yeah, with our currents. You want to pick number 1 first? What equation can you get from that? What we have coming in I1, so that's a positive coming in. Okay. What we have going out? I2, so that's a minus I2. And what is I3 doing? Coming in, so that would be a plus I3. And that's equal to 0, way over there, all right? Why? Because we've got 3 more to deal with. Okay, let's go to junction 2. What's I2 doing to junction 2? Leaving, so that's a minus I1. All right, I2 is coming in, so that's a plus I2. And no, I3 is not involved with 2. I4 is leaving, so that's a minus I4. And that's equal to 0. If you account for your signs here, 0 is there. Some leaving, some, okay. Okay, let's go to junction 3. What's the smallest I? 3, subscript I. That's 3. It's leaving, so minus I3. And then the next one dealing with that is I5, and what's that doing? Coming in, so that's a plus I5. And then what's happening with 6? Leaving, so minus I6. And that's equal to 0. Okay, let's go up to 4 and see what happens. Smallest number subscript would be 4 here. And what's that doing? Going in, so that's a plus I4. Minus I5. Plus I6. That's equal to 0. All right, we've got 4 unknown currents. 6 unknown currents and 4 equations. So we need at least 2 more, okay? Now they draw 3, and the reason is, I think, that those are so intertwined there, I bet you there's some redundancy there, some, what's a better word for it, dependency there. So I'm guessing we do need all 3 loops. We actually have more than 3. They did 1 loop here, 1 loop here, 1 loop there. There's a loop on the outside if you wanted to do it. There's a loop between these and a loop between those. There's a bunch of loops. But the simplest is just keep it the isolated one. Let's just do that. Now, which direction does it look like in loop 1? That looks pretty reasonable to have it going in that direction, doesn't it? Because there's your 10 volts positive. Okay? Over here, you just have 1 voltage thing there, so let's go that loop that way. And over here, it looks like it's going that way. Let's see if our currents are agreeing. 1's going positive, 2's going in the right direction up here, 4's going in the right direction, 5's going in the right direction, 3's going in the right direction, 2's going, yeah, that looks good there. Up here, I6 seems to be going right, I5, they look like everything is heading in the right direction to me, but who knows, I may be wrong. So let's start here, and let's have our voltage increases on one side, the decreases on the other. We'll keep everything positive. Okay? So starting at 2, what's the first thing you hit? Yeah, a volt increase of 10. So that's going to equal 10. Then we hit a voltage drop, and we'll put it on the other side and keep it positive. And what would that drop be? 2I1. So here we have a 2I1. But then on the way around there, we run into another resistor, and what would that be? Voltage drop of 4I2 plus 4I2, and that's equal to 10. Let's go to that busy one in the middle. It really doesn't matter where you begin. Let's begin at 2 again and go around. First thing you hit is a, if you can read my writing, I think it's a 17. Yeah, 17 volts boost there. Let's see the drops that we have. First one we hit is 2I4. Okay. Next one we hit is plus 2I5. And the next one we hit is I3 just by itself, plus I3. Okay. And then we have one more. 4I2. Okay. And that's equal to our 17. Those are our voltage drops, 1 voltage increase in that loop. Let's do the other loop over here. And you can start anywhere you want to. I don't see. Let's just start up at 4. What's the first thing you get? Yeah, a drop of 2I5. And since we've got the drops on the left-hand side, we'll keep it positive. And then we hit A, and that'll be another drop, plus 4I6. Okay, and then we hit A equal 14 volts. That's your bump on the other side. Okay, what you want to do with this? Do a matrix. It's going to be a big, hairy matrix. So give me the first row. 1, minus 1, 1, 3 zeros, and a 4th zero. Okay. Second one's going to be a minus 1, 1, 0, minus 1. And then 3 more zeros. Third one's going to be a 0, 0, negative 1, 0, 1. No, negative 1, isn't it? And a 0. Okay. Fourth one's going to be a, help me, 0, 0, 0, 1, negative 1, 1, and a 0. All right, the fifth one's going to be a 2, 4, and a bunch of zeros, 4 zeros in a row, and a 10. Next one's going to be 0, 4, 1, 2, 2, 0, and a 17. And the last one's going to be a in fact, that's 4 zeros, isn't it? I1 through I4 are zeros, then you have a 2, 4, and a 14. Now, anything here strike you something you could do right at the top to ease the situation a little bit? This one you can divide by 2. That you can divide by 2. So can I just do that without rewriting everything? Please say yes. Okay. So this will be a 1. I won't do it one at a time so I don't do anything stupid. The 4 becomes a 2. 10 becomes a boy, folks at home didn't know that was coming, did they? Okay. That becomes a 5. And in the last row, 2 becomes a 1. 4 becomes a 2. Didn't pick up the eraser. Okay. And the 14 becomes a, help me, 7. Okay. Okay. System's pretty slow though as well. Okay, what's the first thing we want to happen? One in the upper left, cha-ching, we got it. Okay, what do we want to happen next? Zeros below it. How do we make a zero happen here? Add row 1 and 2. So row 1 plus row 2. I'm not going to write it down because I don't have room. Okay, so we're going to leave row 1 alone. 1 minus 1, 1, and 4 zeros. Okay. Ooh, that's an ugly 0 there, isn't it? My pen's not writing well, so I don't see what it looks like. Okay, so add those 2 rows together, and what do we get? 0, 0, 1, negative 1, 0, 0, 0. All right. And then the next 2 are already taken care of, so I'm going to write those down. 0, 0, minus 1, 0, 1, minus 1, 0. And the next one's taken care of. 0, 0, 0, 1, minus 1, 1, 0. All right. What do we want to happen to this one? Okay, row 5 minus row 1, and that would be a 0. Second? 3? Is that what you said? Okay, I can't hear well. Negative 1. Okay. Lost myself here. Next. 0. 0. 0. Goodness, you're stuck, aren't you? How many have we got there? Wait. All right. Sorry. I think AC kicked in and it's blowing right down on top of me. So that was 0, 3, 0, 0, 0, 0, 4 zeros there, I think. No, 3 zeros, and then a 5. Is that right? I got that 0 out of line. Okay, believe that's right. And then the next 2 rows are perfectly fine. 0, 4, 1, 2, 2, 0, 17. Ooh, that looks out of place, doesn't it? And a 0, 0, 0, 0, 1, 2, 7. Okay. Now, what do we want to happen next? Oh, yes. We want the first non-zero entry in the next row to be a 1. Well, that happens here. Well, it could happen here, but we need one of these 2 rows to move up there. Now, do you have a preference of which you'd like to move there? I like row 4 because you could write those as decimals if you you wanted to. This one would be not easy to write as decimals. So I would swap row 4 for, I think I would just drop down the others, move row, whatever that is, 2, 3, 4, 5, 6. Row 6 up there, drop everything else down. Okay? And you can see you got a bit of work to do. And while you're doing that, you need to divide by 4, so this would be a 0.25, 0.5, 0.5, 0, and that would be 6.25. Okay. If you want to use decimals, if you want to use fractions, then it's fine too. So that would go up here. Then you only have one row to change the number there. Well, two, one above and one below. But they would be relatively easy to do. Okay? You want to take most of the rest of the class doing this? Really, we'll go along pretty quickly, but it's some work to do. What they do is using Gauss-Jordan elimination, a graphic utility, or a software program, solve that system to obtain blah. Okay? Now what they have, as we did, 1, 2, 3, 4, 5, 6, 7, but only 1, 2, 3, 4, 5, 6 unknown. So one of the rows does wind up being all zeros. Otherwise you wouldn't have a solution. Okay? And it's just, it will take a long time to do it. Are y'all comfortable carrying on from here? I'll do the next step because I do have room to put it in. No, I really don't, but I'll move this row up to there. That's not good notation, but that's what I'll do. Okay? That would be a 1, minus 1, 1, 0, 0, 0, 0. Okay? The next row will be a 0, 1. Now, do you prefer fractions or decimals? I don't really care. Decimals. 0.25, I'm going to leave off the leading 0. But I wish my decimal would show up. There it is. 0.5. 0.5. I hope you see the point there. Okay. A 0 and a 4.25. Okay. It's a mess. And then the rest of them just move down 1. 0, 0, 1, minus 1, 0, 0, 0, 0. Goodness gracious, this thing's such a pain in the neck. That's a 1 and a minus 1. My pen wasn't writing as fast as I was, and it didn't show up as well. Okay. Something's wrong. Okay. 0, 0, 1, minus 1. That's what's wrong. There's your minus 1. Okay. Well, it's not right. There it is. Okay. All right. I think that's right now. And then the rest of them go up to that 0, 0, minus 1, 0, 1, minus 1, 0. Okay. This is such a pain in the neck. It just wants to turn to the next page for no reason. And then the next one would be a 0, 0, 0. 1, minus 1, 1, 0. Goodness gracious. And then the next one's your 0, 3. Goodness gracious, this is aggravating. -1, 0, 0, 0, 5, 0, 0, 0, 5. If I write enough, fast enough, then it. And then the last row is that last one, 0, 0, 0, 0, 1, 2, and 7. Okay. All right. So the next step would be to add these two rows together to get that. So your decimals show up there. Then this row minus 3 times that row. Then your decimals show up there again. And then you got all zeros above and below that. Then you have this as your leading one, and you can get rid of the things above and below there pretty easily. Okay. And then what I think I would do is flip these two rows and have that being the leading one, and go from there. And then I move this one up and have that one. Yeah. So I would keep it trucking. Of course, by this time we may have had other things mess it up. But it's fairly easy to move it along. It's just going to take probably another board full. And anyway, what they say is they come up with 6 currents. I1 is 1, I2 is 2, I3 is 1, I4 is 1, I5 is 3, and I6 is 2, which then those represent the number of amps. They're fun. I wish we had time to do the whole thing, or board space. If I had the whole boards, I would do it, but then I wouldn't be recording for those people who want to. So homework exercises here. By the way, answers to the odd number problems are in the back, but also calcchat.com, a free website, has worked out solutions for the odd number exercises. So you have 2 ways to check your answers. Check them in the back, see if you can figure out where you went wrong. If you can't, then you can go to calcchat.com and see exactly where you went wrong. So do any of the odds 1 through 11. And then do any of the odd, I'd say either 13 or 15 or both. 17, 19. There's a proof at 21. You can choose to do it or not. 23, 25, network analysis, either 27 or 29. No. Okay. Then in Kirchhoff's law, either 31 or 33. And then there's a temperature one, another network, 35. And I don't know if you remember back from Cal 2 where you did partial fractions as a technique for solving integrating or solving some integrals. There's 37 that's a partial fraction problem. And then from calculus, eigenvalues type thing. Well, no, I'm sorry, this is a Lagrange multiplier. They use the same symbol for it. That's number 39. Now, if some of those upper level numbers take too long or get you too wound up into knots, you can forget about it, because most of your problems are going to be able to do fairly simply within a reasonable amount of time. You also have some review exercises. Those also have the odd number. Let's see. Yeah, I think the review exercises also have odd answers in the back. Let me just make sure. Pretty sure that's the case. Yeah, odd answers in the back, and odd answers at calcchat.com. So if you need some more to review everything, any of the odds 1 through 5, number 7, any of the odds 9 through 19, number 21, 23, either 25 or 27, any of the odds between 29 and 37, either 39 or 41, 43 or 45, and any of the odds 47 to 50, either 47 or 49, or both. Number 51 is talking or writing or thinking through that. 53, little, pretty simple, I think, but I'll let you decide whether you want to follow it or not. There's a true false on number 55, 2 parts to it. And then there's a sports application on 57, partial fraction, another one of those at 59, polynomial curve fitting, 61, sales, 63, population, 65, a network analysis, Kirchhoff's law, 67. And then there's projects if you want to look at those, you can. Any questions? Chapter 1. Did everyone get a copy of the test, or did I gave those, didn't I? Okay. Everybody got one? Okay. There's one person who added to class. I've got to figure out a way to get him one. So I think he has emailed me, so I can email back. All right. Yes. What's that? Yeah, I thought so. I have absolutely no control on the thermostat. It's all controlled somewhere else, and I don't know. It's a pain. They used to have a thermostat I could adjust there, and each room had its own control. They went to a centralized system, and they don't let us mess with anything. All right. That is it for Chapter 1. You've got your test. Try to have it back to me in a week if you can. If you need longer, it's okay, but try to get it back to me within a week if possible. Okay, now we're going to matrices in Chapter 2. Oh, what a surprise, as if we haven't been doing matrices. But this time we're going to talk about operations of matrices, properties of matrices, inverse of a matrix, elementary matrices, and applications of matrix operations. We may do a little bit less on the 2.5 because we're moving a bit too slowly. So let's first talk about, we know what a matrix is, an array of numbers, right? So many rows, so many columns, an entry in every place, right? So, here are some general nomenclature type things. Usually we represent a matrix with an uppercase letter. Capital A, capital B, capital C are the favorites, okay? Now, the individual elements, let's say we have a matrix we're saying is A, okay? Matrix A. Now, it will have so many rows and so many columns, and everything has to be covered. We can represent in shorthand that matrix as A sub ij, okay? Where I goes from 1 to the number of rows, j goes from 1 to the number of columns, okay? So that little nomenclature there represents the whole matrix. That would be A11, A12, A13, A14, A1 up to A1n, A21, A22, A23, A22, blah, blah, up to A2n, A31, A32, A33, up to A3n, and you go down through A M1, A M2, A M3, A M4, dot, 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 until you get to A Mn. That represents them all in that one little symbology, where I goes from 1 to M, and J goes from 1 to N. Okay. So, well, I just said all that. The other way to represent it, I was hoping not to have to write this, but I'll write it. A11, A12, A13, dot, 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 to A1n, I think they call it. Yep. A21, A22, A23, dot, 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 up to A2n, A31, A32, A33, dot, 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 up to A3n, and dot, 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 down to A M1, A M2 with a dot, 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 and a dot, 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 A M3, and then a dot, 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 and a dot, 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 and dot, dot, everywhere, a dot, dot. We have A M N. So that's the shorthand notation for all those. M rows, N columns. That's your rectangular matrix with something representing every element. Okay? Now, what would we mean if we said that two matrices are equal to each other? What does that mean? Let's say we have matrix A, which is Aij, and matrix B, which will be called Bij. Now, two things have to be true, at least two things have to be true for those two matrices to be equal to each other. Number one, they've got to be the same size. They both got to be M by N's. One can't be an M by N, the other an N by P, or something like that, with those being different numbers. Just can't happen that way. You would have some elements without anything to compare to. So number one, they've got to be the same size. Number two, then, every element. A11 has to equal B11. A12 has to equal B12. Every element in every matrix, in each matrix, all of your corresponding A's here would have to be exactly the same as your corresponding B's. Say B32 has to be the same as A32. B73 has to be the same as A73. Every one of them has to be identically the same. So they have to be the same size, and they have to have corresponding elements. Okay? So I'm going to write that out because a few of you still don't have your text. Two matrices A equal Aij and B, which is equal to Bij. The I's and J's go to the same limits there, are equal when they have the same size That's the first thing. Exactly the same size, M by N, whatever that happens to be, they can't be different. And Aij is equal to Bij for every I1 less than or equal to I less than or equal to M, and 1 less than or equal to J less than or equal to N. That's the easy way to say it. That is an M here and an N there. They just keep getting worse and worse. Okay, let me clean those up. That's an N. Okay, for every corresponding element. If the I's and the J's are the same, those A's and B's are identically the same. Okay, that's what makes for an equality of matrix. Okay, now, get used to these notations because they're going to do a lot of their proofs, a lot of their examples using those notations. So here's example 1. Goodness, my head is all clogging up. I can hardly breathe. Here are 4 matrices. A, 1, 2, 3, 4. Pretty creative matrix. Okay. Here's B. Notice the capital letters represent the matrix. 1, 3. Here's C. 1, 3 this way. D. 1, 2, X4. Okay. Can A and B be equal? Why not? Not the same size. Can't possibly be equal. Okay. Can A and C be equal? Huh? A and C. No way. Okay. Same reason, not the same size. How about B and C? They're the same numbers, but they're not the same size. B is what size? 2 by 1, what is C? 1 by 2, not the same size, okay? Same entries, same number of entries, but they're not the same size, okay? We call B a column vector or a column matrix. C could be called a row column or a row matrix, okay? So that doesn't make sense. A row vector or a row matrix, okay? Now, could either B or C be D? No, wrong size. Could A and D be equal? They could be on one condition. X has to be equal to 3. If X is anything other than 3, they're not equal. But if X is equal to 3, yes, they are. They're same size, and then every entry would be the same. But D has a variable in that, so it would be true only if that variable X were equal to 3. So you're absolutely right. So, as I said, B is called either a column vector or a column matrix, and C is called either a row matrix or a row vector. Okay, so that's a column, that's a row. And a vector is a single array of numbers with only one dimension, either rows or columns, but only one dimension. Okay. Now, they bring up something else that is, you don't run into this again until way later in the course. Okay? Here is B. Let's come up with another, let's call it E, matrix E, and have that be another column matrix or column vector 2, 4. Okay? Now, A could be partitioned into 2 column matrices or column vectors B and E. Okay? Which means also, and we could call this one, if you name it a vector, then a vector is usually written with boldface in the book. I can't write boldface, so I put a vector symbol over it. The direction's not involved with it here, and this could be vector A2, okay? But I can't write bold, so I put the arrow over it. And then you could say that matrix A is equal to the vector A written with, partitioned with vector A2, A1, like that. And let's see, do they put the matrix bracket on either side of that? We aren't going to do that for chapters from now, so I'm really surprised they bring it up here, but it's true. It's absolutely true. Now, that covers the equality of matrices. Do you think you can add matrices? Yes. There has to be at least one very important condition. They have to be precisely exactly the same size. Otherwise, you can't add them. Okay? So, how about subtracting 2 matrices? Yep, same thing, same requirements, exactly the same size. And then there's another thing we call scalar multiplication. We'll get to that. So let's do matrix addition first. Now this is the definition. It's full of weasel words, but here's how we define it. If you have matrix A, which we identify as Aij, and matrix B, which we identify as Bij, and in this case, the i's go from the same values 1 to m, and the j's go from the same values 1 to n. Precisely the same. That guarantees they're the same size matrices. Okay? And we'll say those are m by n matrices. Rows by column. That's what m by n stands for. then their sum is also an M by N matrix, got to be, and that sum of A plus B would then be correspondingly Aij plus Bij. In other words, you add identical positioning, not the identical numbers, but positioning. A11 is added to B11. A12 is added to B12. A13, all the way down. You add, so the same I's and same J's are added for every element in that from I to J. I going from 1 to M, J going from 1 to M. But you only do them when they're the same subscripts in exactly the same order. That's what the only things that you can add. Okay, so let's do an example here. These are really hard, folks, so put on your thinking caps. There's a matrix. See if we can add it to this matrix. Can you? Can you just write down the answers? What would you have? 0, 5, -1, 3. Perfect. Okay. How about these two? Can you add those two matrices together? What do you get? 0, 1, -2, 1, 2, 3. Perfect. Now what do you notice there? Okay, first, you can't add them because they're exactly the same size. They're both what size? 2 by 3, exactly, okay? So you can't add them, okay? Now this matrix here has a special name. Anyone want to hazard a guess what it might be? The zero matrix, exactly. And there's not just one zero matrix. This is a 2 by 3 zero matrix. You can have a 3 by 2 zero matrix. You can have a 2 by 2 zero matrix, a 3 by 3 zero matrix. Any size you have, if every element is 0, it's a zero matrix. And here's a way you can express this pretty easily. If you happen to name this, what name would you like to give this one? A, okay. A plus the zero matrix is A, provided the zero matrix is the same size as the matrix A. As long as those two are the same size, A plus zero matrix is always A, okay? It kind of acts like the number 0 in adding real numbers, right? Add any number to 0 and you get the same number. Add any matrix of the same size to the zero matrix of that size and you get the same matrix. Okay? That was B. Can we do C? I think I'm going to have to go to a clean page to do C. Okay? -1, -1, no, -3. I can't read and write and chew gum at the same time. 1, -3, -2, plus -132. Can you add those two matrices? What you think? Okay, you said a 0, 0, 0. Now what do you notice about these two matrices? Number one, they're the same size, so you can't have them. So that was the answer to my first question. Can you do it? Yes. They're exactly the same size. What size are they? Second? 3 by 1, exactly. Now, the other thing to notice here, if this you happen to name, what do you want to name this one? A. Okay, I thought you might say that. What do you notice about A in this one? They're exactly the opposite sign, so you can say A plus negative A, that would be that opposite sign, is always going to be the zero matrix. Just like 7 plus negative 7 is always going to be the number 0. Okay? So you see a lot of connections or comparisons between addition of matrices and addition of real numbers. Okay? Now, let's do a D one. Okay? 2, 1, 0, 4, 0, negative 1, plus 0, 1, negative 1, 3. What does that result in? Say again? You cannot add those because they're not the same size. So that doesn't result in anything. That's undefined. Can't do it. All right. Now, any old matrix you happen to have has elements in it. The very simplest matrix is a single 1 by 1, and that just has one element. All the rest of them have more than one element. Okay? Those elements are just numbers or letters or whatever. Okay? But you can take that matrix, which is an array of numbers, and you can multiply it by what we call a scalar. Now, in some senses, a scalar is just a number, and that's exactly what it is. But the reason they use this term scalar, especially if you're dealing with vectors multiplied by a number, that number is going to change the length of the vector. It scales it up if the number is greater than 1. It scales it down if the number is between 0 and 1. It reverses the direction if it's a negative number or opposite sign from a negative number, and you multiply it. So that's why they call it a scalar, because it scales up or down. Okay, so when we're working with matrices, real numbers are referred to as scalars. Okay, usually if they're not an element in a matrix. Okay, so to multiply a matrix A by a scalar C, we multiply each entry by C. Okay, here's how we say that. C times the matrix A would be the new entry CAIJ. So notice every entry in there gets multiplied by the C. Okay? And that's a pretty big deal because you're not just multiplying one thing by C. Every entry in there is multiplied by C. Okay? So let me write that there. I just said it. If well, it's not going to make a lot of difference. I mean, I just said everything that's written here. If A is equal to the matrix Aij is an m by n matrix, C is a scalar, then the scalar multiple of A, C times A, is C times every entry. When I goes from 1 to m, j goes from 1 to n, every entry gets multiplied by C. Okay? Now, a very special case of that, what is negative A? Negative Aij. In other words, you negate every one, just like up here. If this is 1, negative 3, negative 2, when you negate that, that becomes a negative 1, positive 3, positive 2. So that would be an example of A 1j, because this only has one value for I. And then negative A 1j would be your opposite. Now, get this. If A and B are matrices of the same size, okay, same size, and quite often for same size, rather than having to write that off, we just say m by n. They're both m by n. Same m, same n, okay? Then if you're subtracting the two matrices, A minus B, all that is A plus the negative of B. Just like it was with adding sign numbers. Subtracting sign numbers. If you're subtracting a -3 from a -7, you change the sign of the second number, make it -3 plus 7, and then add those. Okay? So, let's do example 3. Here's matrix A. 1, 2, 4, -3, 0, -1, 2, 1, 2. Here's matrix B. 2, 0, 0, 1, -4, 3, -1, 3, 2. All right. First thing I'll ask you to do. What is 3A? Can anyone just call it out to me? The elements. 3, 6, 12, -9, 0, -3. Is that what you said? Yeah. 6, 2, 6. Oh, yeah, 3. Sorry. 6, 3, 6. Okay. You're lulling me into just listening and not thinking. Okay? That's the A part. Okay, the B part says, what is -B? Can anyone tell me what that is? -2, 0, 0, -1, 4, -3, 1, -3, -2. Perfect. And can anyone else tell me what C is 3A minus B? One. You say 6? Yep. 12. Is it -10? Okay. Here's what I'm doing. See, I'm being real cheaty about it. Okay. Okay. What you did was 3 times A was -9 minus a 1, which would be -10. Since this is 3A and that's minus B, I'm just adding those, which is a really easy way to do it. Okay. Or you can do it, go back to the beginning. Either way. But your delay there let me know you were doing that. What does the next one be? 4. 0. Yeah. It'd be 3 times -1, it would be -3 minus 3, which is -6. 7, 0, 4. Perfect. There is your C part. Let's make sure they got it right. Good for them. Good for them. And good for them. Got it. All right. So we've seen we can add, we can subtract matrices. We can multiply matrices by a constant multiple, a scalar. Okay? Can you multiply two matrices together? You can, but it's not nearly as easy as adding and subtracting. Nowhere close. Can you multiply two matrices together that are not the same size? Yes, you can. You can't add or subtract two matrices that are not the same size. Can you multiply any two matrices that are not the same size? No, they have to have one thing in common. Okay? And they start this with talking about why not, football stadium, okay? They must be from Alabama, huh? This is the most important thing going. What if we have 3 stands of a football stadium? For some reason, there's nothing on the east side of the stadium. Maybe that's just open to the open air. So we have 3 sides of the stadium. They have the south stands, the north stands, and the west stand. Okay? And at each stand, they're selling, have a concession stand. In fact, these are the stands, the north, south, and concession. Whether the football field has seating there or not, 3 concession stands, north, south, and west, no, not on the east. And at each concession stand, they sell peanuts, hot dogs, and soft drinks. Or, this must be from the north, sodas, okay? Down south there, Cokes, they're soft drinks or whatever. Now, each of these also has a selling price, okay? All right. Now, in the selling price, the first row represents the selling price for peanuts, the second for hot dogs, and the third for your sodas, okay? Now, this one game, South Stand sold 120 bags of peanut, 250 hot dogs, and 305 sodas. I say 305 and write 350. There's something wrong with my brain. Okay. Okay. The selling price was $2, $3, and $2.75. $2 for peanuts, $3 for hot dogs, $2.75 for a soda. Sounds like a rip-off. Sounds like a stadium. Okay. North Stand sold 207 bags of peanut, only 140 hot dogs. Cheap people live over there, but 419 things. And that sort of makes sense because the north side of the field is going to have the south sun shining on it. So they got thirstier. No, that's beside the point. The west stands, really cheap folks over there, 29 bags of peanuts, 120 hot dogs, and 190 sodas. Okay? Now, if you're trying to figure out how much money did you make and do it per location, and that's what you can do. In the south stands, you can multiply 120 bags of peanuts by $2 each, 250 hot dogs by $3 each, 305 sodas for $2.75 each, and that would give you the money you made from the south stand. Add them up and you get the total. On the north stand, 207 times $2 each, 140, 419 times this. Okay? 140 times 3, 419, about 275. In the west stands, 29 bags of peanuts, $2 each, 120 hot dogs at $3 each, and 190 sodas at $2.75 each. So multiply those together. And then you get a matrix, which is your result matrix, which would be how much money you made. Okay? And from the south stand, whatever that number came to, north stands whatever that number came to, and the west stands whatever that number came to. And there you would have a resulting matrix. Guess what we just did? Matrix multiplication. Now, a few things to note here. What was the size of the first matrix? It was a 3 by 3 matrix. What was the size of the second matrix? 3 by 1 matrix. And what was the size of the third matrix? 3 by 1 also. Okay. Now here's the key, folks. And it's not, this doesn't prove it, but it's true. When you list them like this, the second number, the number of rows in the first matrix must equal the number of columns in the second matrix. Otherwise, you couldn't multiply them, could you? Could you have multiplied a 3 by 3 by a 1 by 3? No, it won't work. These two numbers have to be the same. And since they're the same, wipe them out, and guess what your resultant matrix is? A 3 by 1. Okay, so number one, the sizes matter here. These two have to be the same numbers here. The second dimension of the first matrix, the first dimension of the second matrix have to be identical, otherwise you can't multiply them. And if they are identical, and they are, then eliminate those, and what remains is going to be the size of your resultant matrix. Okay? Every time. So this just happens to be the second and the result are the same. That's not always going to be the case. Make up different numbers here. Give me two numbers. 2 by 2. Okay? What would have to be the first number of that? 2. Make up a second number. Okay, you made it the same as this one. Okay, it's fine. How about a different second number? 5. A 2 by 5. Can you multiply those? Yeah. 2 by 2 times a 2 by 5. Yeah, the 2's are the same. And what's your resultant matrix? 2 by 5. Now that's because you had the first number being the same here. Give me two different numbers here. You need two numbers.
8 by 9.
Second?
8 by 9.
Okay, this is an 8 by 9. What has this number got to be? A 9. And give me a different number out here. 6. A 9 by 6. Can you multiply 8 by 9 by 9 by 6? Sure you can. And what would be your answer? Resulting matrix? And 8 by 6 has nothing to do with, nothing is replicated there. So yes, the two inner numbers of those two sizes have to be the same. Eliminate those, and the outer numbers give you the size of the resulting matrix. All right. I know, that's so sad, isn't it? Do you want to multiply those out next time just for fun, or you can do it at home, or they did it in the book. I'm just asking, do you want to do it for the practice of it? Yay or nay? Yay, okay. We'll do that next time. We'll actually multiply those two out. Okay? Homework exercises here. Let's see if we got far enough you could do that. I'm sure we did. You can do either 1 or 3 or both. You can do any of the odds 5 through 11. You could do 13 or 15 or both. Well, do 13, do 15. They're two separate type problems. And then we'll hold off doing the rest of those till next time. Okay? Good deal. Continue working on your test and proceeding with finishing 2 and 1 and working on 2. And we'll see you on Thursday. Good deal.